So good afternoon, everyone. First of all, I would like to thank the organizers for inviting me here. It's a pleasure to be in Kyushu again. So I work for two French institutions, Inria and CNRS, but I'm based in Tokyo. So I moved 6 months ago. So I want to tell you about lattice-based cryptography this afternoon. And before I start my talk, I would like to say that I'm very excited by what is going on. 10 years ago, we organized with the eCrypt network the first PostQuantum Cryptography conference. And I don't think we expected things to turn out this way 10 years after. And I think that for everyone interested in post-quantum cryptography, this is a very exciting time, because if there's this competition, I think it will really improve the state of the art. We will really understand things better after the next couple of months. So when I prepared these slides, I realized that I was way too ambitious. There's way too much material to cover. So I had to make a lot of choices. So today I wanted to cover both design aspects and cryptanalysis aspects. The 1 hour and a half is very short, so I apologize, I will miss a lot of things. I will only describe, I want to give you a taste of these few topics, but I will not be able to go into details for any of these things. So first I want to introduce lattices. So the first thing to say about lattices is lattices are very simple objects, but they have been studied by very serious people. So they appear almost everywhere in mathematics. You see them in algebraic number theory. You see them in algebraic geometry. There are deep problems in algebraic geometry related to lattices. You see it in sphere packings. A couple of field medalists have studied lattices. So Margolis, Lindenstrauss, Smirnov, and more recently Bhargava all studied lattices. There's a lot of application of lattices, not just in computer science, as we know, but also in statistical physics. So it's a really interesting topic. When I started my PhD was almost like 20 years ago, and I was already doing lattices. And why am I still doing lattices now? Because it's really a fascinating question. There are so many things, there are so many angles you can view lattices that it keeps it interesting. Okay, so this is a serious thing, but it may not be so serious when you try to see what is a lattice. So intuitively, a lattice is just an infinite arrangement of points which are somehow regularly spaced. So because post-quantum cryptography is in Japan, I think it's good to take an example from daily Japanese life. So you'll see an example in games here, an example in restaurants. So maybe tonight we'll see something like that. So these are salmon eggs. And you can see that all these eggs are somehow regularly spaced. So this is the beginning of a three-dimensional lattice. So more formally, a lattice is a discrete subgroup of R to the n, which means that we're going to take a subgroup of R to the n, and every point will be isolated. So for any point, I can find some ball such that there's only one lattice point inside. So that's one way of defining lattices. That's the usual definition in math textbook. Another definition is more computer scientist, I would say. You pick some linearly independent vectors in the space, and you consider all the linear combination of these vectors with integer coefficients. Okay, so for instance, you could say, I'm going to pick this matrix, and I'm going to take all the linear combination of these rows with integer coefficients. So that's a very concrete description of a lattice. And both definitions are equivalent, so I can switch from one to the other. It is good to know both. It's good to be familiar with both. But this is really the general case of a lattice. In practice, especially when we deal with cryptography, we don't deal with arbitrary lattices. We deal with special cases. We deal with integer lattices. So integer lattices are easier to define. Usually, we're going to restrict ourselves to any subgroup of the integer vectors such that the quotient is finite. Okay? So it's very simple to check. You take a subgroup. So you check any subset stable by subtraction and non-empty. And you want to make sure that the quotient is finite. So here's the first trick but it's important to remember, even though a lattice is infinite, so you have infinitely many lattice points, so this is a bit unusual in cryptography. Lattice cryptography does not work directly with the lattice. It actually uses this finite abelian group, this quotient of the integer vectors divided by the lattice. So this is one thing to remember for the intuition. Lattice cryptography works modulo lattice. Okay? We don't work directly with the lattice. We need a couple of things to get familiar with lattices. So here are some invariants. The first invariant is the dimension of the lattice, which is the dimension of the linear span of the lattice. So here would be an example in dimension 2. And related to this, you can define the co-volume as the volume of any basis parallelepiped. So remember I said any lattice is the set of the linear combination, integer linear combination of some fixed vectors, and these fixed vectors are called a basis. So here are 3 examples of basis: a green basis, a red basis, and a blue basis. And I can take the volume of this parallelepiped. That's the volume of the lattice. It does not depend on the basis. It's actually the measure of the quotient between span of L divided by the lattice. And if you're given a basis, there are some simple formulas to compute it in polynomial time. So the simplest lattice would be Zn, and its volume is 1. Okay? So why am I defining it? I'm using this invariance because I want to give you a first intuition, which is very useful, is the Gaussian heuristic. So the Gaussian heuristic says that the volume, which we just defined, measures the density of lattice points. So for a nice lattice and for a nice set, we often estimate the number of lattice points inside the set as the ratio between the volume of the set divided by the volume of the lattice. So for instance, in this picture, I would take this ball. And you can see that it looks approximately correct, that the number of lattice points is essentially the volume, the area of the ball divided by the volume of the lattice. But this is a heuristic. It may not be true. This is just an intuition. Sometimes it's going to be true. Sometimes there's going to be a theorem. Sometimes it's completely wrong. Sometimes it's completely off. Okay? This is just an intuition. So how do we use this Gaussian heuristic? We need to know some volume of appropriate sets. So for instance, if I consider a well-known exercise, at least in France, computing the volume of the n-dimensional ball of radius r, we have this famous formula of the gamma function, and we get this asymptotic equivalent. So using this equivalent, I can easily guess now if the Gaussian heuristic is true, when do I have lattice points? Okay. So when does a ball of radius r contains many lattice points or no lattice point? So using this formula, for instance, that I would expect that in an arbitrary lattice, if I take this radius, you can see that the ratio is exponentially high. So I would expect there's exponentially many vectors. Okay? But again, this was the heuristic, but it is a theorem. There's a theorem that says any d-dimensional lattice has exponentially many vectors of norm this. Okay? So this bound, this threshold is quite important. On the other hand, if I decrease the constant here, by the same Gaussian heuristic argument, you would expect that this ratio here is extremely small, much smaller than 1. Therefore, I would expect there is no lattice vector. Of course, in the worst case, I can build a lattice for which the first minimum, the shortest vector, is very, very short. But in a random lattice, this is true. In a random lattice, all non-zero vectors have norm bigger than some constant times the same threshold here. So I will not enter into the theory of random lattices. There's a beautiful theory of random lattices that shows a lot of interesting properties of random lattices. I'll just say this is a real theorem. There's a real theorem that says in a random lattice, this is bound. So what we need to remember now is this threshold, square root of d times d foot of the volume. That's where things get interesting. Okay? So it gives us an intuition of when do we say that a lattice vector is short or not. That depends on this quantity. So in mathematics, historically, people were more interested in a worst-case scenario. So there, in particular, the so-called Hermit Constant refers to the worst case for these short lattice vectors bound. So Hermit in 1850 showed the existence of this constant. So you consider the shortest vector, the shortest non-zero vector, shortest norm, so it may not be unique, and you divide it by the d fruit of the volume, where d is the dimension. And Hermit showed that this quantity is upper bounded for a fixed dimension. It can be upper bounded independently of the lattice. So this is Hermit constant. Okay. All right. So now we saw the basics with lattices. Let's see about what do we know about harness of lattice problems. So essentially, these lattice problems have been studied a lot for the past 20 years. So you'll see a lot of articles in Stark Fox studying the harness of lattice problem, both in the classical model and the quantum model. And this is what we get. We get that for, depending on the approximation, if the approximation factor is very small, these problems are essentially NP-hard. So we don't expect them to solve them efficiently. On the other hand, if we relax our problems up to square root of the dimension, these problems become non-NP-hard, which does not mean that we can solve this problem, but it's unlikely to be as hard as an NP-hard problem. And if we relax even further, if we go to a linear factor in the dimension, then we have this worst case to average case reduction. And if we relax even more up to some polynomial factor, then we can do cryptography. So for lattice cryptography to be meaningful, we need these problems to be hard. On the other hand, our margin is not so great because we know that there are polynomial time algorithms that can approximate these lattice problems up to some sub-exponential factor. So what are these problems? I didn't mention exactly what is this approximation factor. This is just to give you some intuition. So here is the most famous lattice problem, the shortest vector problems. You're given a basis of some lattice, and I ask you to find a non-zero vector of minimum norm. Okay? So this problem is essentially NP-hard. So we're going to relax this problem. Instead of asking for the shortest vector, we're going to ask a vector whose norm is not too far from the best norm up to some approximation factor. So that's the meaning of this approximation factor. I could ask for this red vector, but instead I'm going to ask for a vector whose norm is not too far. All right. So these are the basics of lattices. So now we're going to switch to introduce lattice-based cryptography. So in one slide, I can explain where does the benefit of lattice-based cryptography come from. So if we remember RSA, so RSA use these large groups, Z and star, where n could be 2048 bits, 4096 bits. So when you see that, you could think that if I want to speed up RSA, there is essentially two strategies. I would have to change of group. So what could I do? I could choose a smaller group for which some problems are hopefully harder, maybe whose operation are actually more expensive for the same bit length. But because my group is smaller, I can still get some speed up. That's exactly what happens with elliptic curve cryptography. We use a smaller groups whose operation is more expensive, but overall, because we select the smaller groups, we are still faster. Lattice cryptography does the opposite. Instead of choosing a smaller group, it's going to use a bigger group. But the operation is going to be much cheaper. It's going to be additions, mod some integer, for instance. Okay? So this is the secret of lattice cryptography, using larger groups on RSA, but with a cheaper operations. So what are the benefits and drawbacks of lattice-based cryptography? So we know that some of these schemes are more efficient than RSA. We know that these schemes are potentially resistant to quantum computers. So there are actually several groups now working on prototype implementation of a lattice TLS. We know that some of these schemes have security properties based on worst-case assumptions. And then the final reason is it's very trendy. So as you may have heard, you must have heard, there's been a lot of recent breakthrough. There's been fully morphic encryption, multi-level maps, and obfuscation. But as you know, things are evolving very fast. So for instance, many of these multi-level maps, maybe all of them have been broken right now. So it just tells you how trendy it is. Everybody is looking into this right now. But not all is well. There's also some drawbacks. So if you look at the literature, there's a gigantic now literature on lattice-based cryptography. But many of these papers do not propose parameters. I mean, apart from N-truth, there's actually very few concrete proposals of parameter sets. So sometimes it's unclear how practical this lattice-based cryptography is. And it could be that maybe this gain is only asymptotic. Maybe it only shows up in very high dimensions. So what is the history of lattices in cryptology? There are 3 years that stand out. 1982 was the first use of lattices in cryptanalysis to break some knapsack cryptosystems. And you could say that knapsack cryptosystems are actually the ancestors of lattice-based cryptography. And then in 1996, there were the first crypto scheme based on hard lattice problems explicitly. So there was N-truth, there was iTie-dwarf, there was GGH, a lot of other schemes. And 2009 is really a big game changer when Gentry introduced fully homomorphic encryption based on lattices. So how do we describe lattice-based crypto now? So as I said, you could view it as somehow a revival of knapsack cryptography dating back to Merkle-Hermann in 1978. People sometimes don't want to do that because knapsack cryptography has a bad image. But I really think that knapsack cryptography is lattice cryptography. It's just the first generation. Many of the ideas used in knapsack cryptography have been reused in lattice cryptography. Obviously, something went wrong in the early 70s, but that's normal. I mean, this was just the beginning. So for a long time, there was essentially two families. There are theoretical schemes, going back to the iTie paper, where the focus was on security proof. Nobody really cared about any parameters. People only care about how good is the security proof. What kind of statement can we make? Rigorous statement can we say about things? And then there is this applied family going back to the N-truth paper, where surprisingly the focus was really on efficiency. I mean, the inventors of N-truth are mathematicians, but they are not interested in security proof at all. They only care at that time on efficiency. So the good thing is, at the beginning, these two families tended to ignore each other. They will not even reference their own papers. But fortunately, this has changed in the past 15 years. So they interact more and more. So there's been a lot of fruitful interaction. And I think perhaps the best example is Gentry fully homomorphic encryption scheme, which really uses ideas from both the theoretical world and the applied world. So now the landscape has changed a bit, because if you look at the lattice-based crypto literature, you see many schemes dealing with problems which are actually not even defined using lattices. So these are SIS and LWE. So these two problems are connected to lattice problems, and they're usually presented with linear algebra. We have matrices, vectors, and accordingly, many of these lattice papers use vectors and matrices. So in this talk, because this is my talk, I'm going to do something a bit different. I'm not going to use linear algebra, so I'm not going to put these matrices. Instead, I'm going to adopt a group theoretical point of view. And I think it has several benefits, and in particular, it clarifies the use of duality in all this lattice-based cryptography. So let's start with SIS. So SIS this problem was introduced by iTie in 1996, but he did not give it that name. So this is the name, I think, given by Michancio later, which stands for small integer solution. So to think about this problem, it's really a group problem. Consider any additive finite abelian group. So let's call it G. And in the original paper, he only considered this group, ZQ to the power n. But it doesn't matter. So you have these finite abelian groups, and now we're going to do something very simple. We're going to generate elements G1, G2, Gm uniformly at random from this group. Okay. So because I use additive notation, when I take 2 times G, for instance, it means G plus G. Okay. So now the problem is to find some short non-zero vectors x1, xm, such that the linear combination sum of the xi, gi, so again as a z module, is equal to the 0 element in the group. So when you take all the integers like this, you see that this is obviously a subgroup of Zm. And you can see also that it's going to be and therefore it's going to be a lattice. Okay, so this set, the set of solution, is a lattice. So you're asking to find a non-zero short vector in this particular lattice connected to the group elements. Okay. So actually, if you think about more, I mean, it's very basic algebra. You can see more precisely that this problem is exactly finding a short vector in a very special class of lattices. It's a uniformly chosen random lattice such that the quotient is isomorphic to the group. Okay, so this is very basic algebra. You can see that the lattice here is of this form, but when I generate my elements uniformly at random, I really get the uniform distribution over these finitely many lattices like this. Okay. So this SIS problem is really finding short vectors in some algebraic class of lattices, okay, where we consider the factor group, the Zm, this factor group we saw before. So what was really interesting about this SIS problem is Aitai 96 proved the first worst case to average case reduction. He showed that if you can solve this SIS problem for this particular group, ZQ to the n, on the average, then you can find short vectors in every n-dimensional lattice. So n, the dimension of the worst case lattice, is the n here. Okay. So a natural question is this a general result for any arbitrary groups? So the answer is positive. It was recently showed that you can generalize this statement to any finite abelian group G, provided that its order is sufficiently large. So there's a condition about the order. For instance, if you take Z2 to the n, it's not sufficiently big. The order does not grow big enough with respect to the to n. Okay. So in some sense, because we obtain a partition of the set of lattices when we consider the factor group, we somehow show that all lattices are hard. Okay, so this is the first problem, SIS. So it's customary also to look at dual problems. So since I took a finite abelian group, it's normal to consider characters. So remember that the character of G is a morphism from G to the torus, so the real modulo the integers. And I'm using additive notation because I'm using lattices to begin with. Then it's well known that our finite abelian group is isomorphic to its dual group formed by all the characters. So we may wonder what happens to our previous lattice. So this SIS lattice, for those who are familiar with the dual lattice of this lattice turns out to be related to this dual group. So it turns out to be related. It's the set of all the vectors which correspond to evaluation of characters at the group elements. So there's this is a very natural thing to do, to consider the dual lattice of my previous lattice, and I obtain characters. Okay. So these bring us to the LW problem. So once I entered the dual, this is what I would like to do. This is a problem introduced by Regev in 2005. So learning with errors. So again, we take these finite abelian groups, and again in the original paper, we restricted ourselves to ZQ to the n. Again, we pick these group elements uniformly at random from the group. But this time, we're going to do something more. We're going to pick a random character with uniform distribution in a dual group. Okay, let's call it S. And now this is the problem. you want to recover that secret character given the group elements, but also noisy approximation of the evaluation of the characters at each group element. So what is a noisy approximation? You're going to take each value and add some Gaussian noise. A lot of various distributions have been introduced in the past few years, but the initial distribution was the following. Take a Gaussian noise here. Okay. So this is not exactly the usual definition of LW, but it's really equivalent. So to make you more comfortable, let's take the simplest case. Let's take a cyclic group. So if we take a cyclic group, it's going to be isomorphic to ZQ. So what does it mean here? It means that we're choosing m numbers at random mod Q, and you're asking to recover a secret number S, given the numbers GIs, and randomized approximation of the multiplication, SG1 mod Q, SGM mod Q. If you're familiar with the cryptographic literature, you realize this is exactly a randomized variant of the hidden number problem of Bonnet and Vekatesen from Crypto 96. So this grouped abstraction is really a way to unify the hidden number problem and also the initial LWE. So you should really think of it as a group problem. Okay? Now, what is great about this LWE problem is that Regev in 2005 showed that if you can solve this problem LWE for that particular group on the average, then you can find short vectors again in every n-dimensional lattice. There's just a catch. This time, the algorithm is quantum. It's not going to be a standard algorithm. And again, recently it was shown that this can be generalized to any finite abelian group under the same constraint that the group order must be sufficiently large, which means that the volume of the average case lattice must be sufficiently large. Okay, what really matters is the volume, the size of the volume. Okay, so these are the basics. So now we can really see how lattice cryptography is built. So I'm going to show you some design to give you some taste of lattice-based cryptography. So if you look back at these past 20 years, we see that there's essentially two types of techniques. There's the first type would be cryptography using trapdoors. So what could be the trapdoor? It could be, for instance, a short basis of a lattice, but not necessarily. And in this situation, we have a lot of similarities with RSA-Rabin cryptography. Okay? But then there's another flavor of lattice-based cryptography that comes without trapdoors. And in this situation, we have a lot of similarities with discrete log cryptography. So here is our first message. In order to understand lattice-based cryptography, it is very useful to be familiar with both RSA cryptography and discrete log cryptography. And it's also good to view these lattice schemes by analogy with these classical public key schemes. So let me give you an example with encryption. And I don't have time to cover all the cases. I'm just going to restrict myself to basic public key encryption. So let's first start with trapdoor-based encryption. So what is the first trapdoor-based encryption? That's RSA. And we get this. So remember, we have a product of two large random primes. We have a public exponent, and we have a secret exponent. And then we have this very basic function, this exponentiation function mod n, which is a trapdoor one-way permutation. And the interesting thing is that the inverse function has the inverse permutation has the same shape. It's raising to the power d. Okay. So what is nice is that for lattices, we're going to have a similar situation. We're not going to have a one-way permutation, but we're going to have a trapdoor one-way function for which somehow the inverse also has the same shape as the one-way function. So it's not going to be a public exponent and a secret exponent, but it's going to be something very close. So to see that, the basic problem that we're going to use is bounded distance decoding by analogy with coding problems. So here, it's a cousin of the shortest vector problem. You're given a basis of a lattice, but you're also given a target vector, which is not any vector. It's going to be a vector in the space very close to the lattice. Okay? It's not a random point. And the goal of the problem is to find a lattice vector minimizing the distance. Okay? So we want to find the closest point once we know that the target is very close to the lattice. So behind it, there's the Voronoi cell. So the Voronoi cell will tell you which lattice point is the closest. So in bounded distance decoding, we're not everywhere. We're only very inside a Voronoi cell. Okay? And by this picture, you can easily believe that this problem becomes easy if one knows somehow a nearly orthogonal basis by either building the lattice beforehand or computing it. Okay. Okay, so that's my core problem. So what can I do with it? So again, I'm going to deal with my quotient. I'm going to talk about reducing something modulo a lattice. So remember, when L is an integer lattice, the quotient is a finite group. And the trick is it has many representations. So that's what we're going to play with. So we're going to call something an L reduction by generalization of the mod Q operation as any efficiently computable map f from the integer vectors such that f of x is equal to f of y if and only if x minus y is a lattice point. So in some sense, L is a period of that function. Okay. So this kind of, I'll show you later how to build this kind of function, but it's a very simple function. Any function that, like this. So if I add the lattice point, it's the same output. Okay. So once I have such a function, I immediately get a one-way function. So I claim that if bounded distance decoding is hard, any L reduction is a one-way function. Why is that? Suppose I want to solve a BDD instance. So I'm giving a target with a lattice. Then T is equal to V plus E, where V is a lattice point, and E is very short because the target is very close to the lattice. Then by definition, F of T is equal to F of E, because T minus E is a lattice point. But so if F is not one way, I could recover, given F of E, I can invert it, so I can recover E, but then I can also recover the BDD solution, because V is equal to T minus E. So saying that BDD is hard is the same as saying that this function, any L reduction, is a one-way function. Okay? I get tons of one-way function from the hardness of BDD. Okay? So now, of course, you could ask, how do I build this kind of L reduction? So it turns out that any lattice basis provides you two L reductions thanks to very classical algorithms, the Babai nearest plane algorithm or the rounding off algorithm. And I will also say that sometimes in cryptography, you also see this kind of reduction. For instance, n-true encryption implicitly uses such a reduction. So let's see how it looks like. So for instance, geometrically, this is your basis, B1, B2. So whenever you have a basis, it generates some parallel pipette here. I take the half coordinates. Okay. Now, my target is here. It's T. So I'm going to choose my image as this vector. So what is this vector? This vector lies inside the parallel pipette in such a way that if I subtract T with the image, I get a lattice point. Right? That's the lattice point here. T minus f of t, that's this point. Okay. So using the parallel pipette, I'm covering the space. And then essentially what I'm saying with this function is I'm just defining which cell I am in, which parallel pipette I'm in. Okay? So that's one way of defining such a L reduction. And you can check that it satisfies my assumption that if I add a lattice point, it's the same output. So it is an L reduction function. Okay? So this is by rounding off. There's also the nearest plane algorithm with a different fundamental domain, and that's how it works. You can see it also in n-true encryption. So this slide assumes that you have seen before a description of n-true. So n-true will use this ring. The secret key is two short polynomials inside this ring. The public key is a quotient mod Q of those secret vectors. A message is a short element in that ring. And you have this, this equation. The ciphertext is the message plus P R times H, where the product is the product in this ring. And R is some sparse element of the ring. So how does it fit into what I'm saying? You can see that actually this function, so because there's already a f, I have to change my notation. Big F of m minus r is going to be this guy. And you can see that this is an L reduction function for this lattice, the lattice corresponding to polynomial satisfying some linear equation here. So even if you don't know it, so this is a geometric interpretation of n-true encryption. Okay? Okay, so we just saw one way. Now we saw that, yeah, we can build easily a one-way function based on the hardness of bounded distance decoding. Okay? And you could ask, okay, what is the benefit of doing this? It's going to be more efficient than in general case. Here, the reduction is very efficient. Now, how do we invert? How do you solve BDD? Well, it turns out that, surprisingly, the same L reduction, when it comes from Babai algorithms, also works in the other direction. So it turns out that if you're familiar with Babai algorithm, you see that they leave some set invariant. So for instance, come back to the picture here. If I take a point which is already inside the parallelepiped, it's the same point. So I'm going to keep my same vector. So suppose that you have some set which is invariant. So f of x is equal to x for all x in the set. Then obviously you can invert, because f of x is equal to x. So you can invert the function. So that allows you to solve BDD when the error belongs to this set. So this is where the quality of the basis impacts your ability to solve BDD, because, for instance, if you consider the largest ball inside this set, it depends on the quality of the basis. So I can invert my one-way function with the same shape one-way function, the same function, but with using a different basis. So that gives you perhaps the simplest deterministic public key encryption. So that goes back to GGH 97 as interpreted by Michencho in 2001. So the secret key would be a good basis that allows you to solve BDD for a good radius. The public key could be any bad basis, such as the Hermit normal form. The message would be a short vector, so that you can solve BDD. And the encryption will be this L reduction, any L reduction with the public key. And the decryption will be any L reduction with the secret key, any good L reduction with the secret key. So this is where your secret key needs to be good. But what is really interesting here in this description is that it's extremely, it looks a lot like RSA cryptosystem. Instead of modular exponentiation with the public exponent, I'm doing a reduction with the public key, the public basis. And then here I'm doing an L reduction with the secret key, just like I was doing an exponentiation with the secret key, secret exponent in RSA. So this is really somehow the lattice analog of RSA. So this is the original, this is the basic general scheme. You can all, of course, try to optimize this scheme by picking special lattices for which these operations become more efficient. And that's exactly what n-true did. So n-true, so encryption fits this framework. You reduce some short vectors modulo the Hermit normal form. But there's a catch. The decryption does not fit this. Decryption is not an L reduction. It's used a special BDD algorithm using the secret key. So using the structure of the lattice, it turns out that you can solve BDD for many errors using the n-true algorithm. So you are more efficient. The encryption is more efficient. The decryption is more efficient. The drawback is that you have to use a special lattices for which maybe finding the shortest vector may not be as hard as worst case lattices. Okay, but that's an example of trapdoor encryption using lattices. So now we can go to trapdoor-less encryption, so something looking more like discrete log cryptography. So what is the origin of discrete log encryption? Discrete log encryption goes back to Diffie-Hellman. So remember, in Diffie-Hellman, you consider a cyclic group generated by some element G of order Q. And because we are in Japan, I've changed a bit Alice and Bob. So Alice is here, and here is Bob. So Alice is going to choose a secret number mod Q, and going to send G to the A, and Bob selects accordingly a random element mod Q and send G to the B. And as we all know, both can compute the shared key G to the power AB. And as we all know too, this key exchange is really the core of L-gamma public key encryption. Once you have this key exchange, you can play with it and make L-gamma encryption. Okay? So I would like to do this somehow with lattices. So for that, I need to understand better what I'm doing. So what am I doing with Diffie-Hellman? There's a natural map here. It's the map that goes from AB to G to the power AB, from ZQ times ZQ onto G. Okay? And you realize it's very easy. This map is bilinear. So in mathematical terms, it's a pairing. It's not a pairing in the crypto sense, but it's a pairing in the math world. And this pairing has a special property. So of course, if you know A and B, you can compute G to the power AB. But the special property of this pairing is that you can also compute it if you hide one of the input with a one-way function. Which one-way function? The discrete log one-way function. The map that sends A to G to the A. So I can compute E of AB using both F of A and B or A F of B. That's exactly what Alice and Bob are doing. Okay? So even if one of the input is hidden by F, I can do my key exchange. And what is the security? The security assumption is that it's going to be hard to distinguish triplets of this form with triplets of this form. And that's a definition of decisional Diffie-Hellman problem. Okay? So now here's an interesting question. If I want to have a Diffie-Hellman analog with lattices, which pairing am I going to use? Which one-way function am I going to use? Okay. Can I have a similar property? Can I find a pairing which can be computed if I hide one of the two inputs, where the input is hidden by some one-way function? So here's the answer. The answer comes from the dual group. So there's a very natural, the most natural pairing coming from the dual group would be to evaluate the character at the group element. But we have to tweak it a little bit to fit our one-way function. So let's pick again m group elements in the group. Remember the dual group G cross. And this is the pairing I'm going to consider. I'm going to pick the first input is a character. The second input is an integer vector. And what am I doing? I'm evaluating the character at this group element. This group element is the linear combination of the GI. Okay? So you can easily check by definition that this is a pairing. It's bilinear in both coordinates. Now, how can I compute this pairing even if the inputs are hidden? So how do I hide the inputs? Well, the most natural thing to do to hide the integer vector is to take the linear combination, because it's already here, right? So that looks a bit like the SIS problem, and that's actually the SIS one-way function, sum of the xi/gi. And I'm going to restrict myself to small integer xi's, okay? And now the second, how to hide the characters. So the character is going to be hidden by adding some noise, just like in LWE. So for this character, I'm evaluating at the group element, and I'm adding some noise. So that's the LWE one-way function. Now, what I claim now is that this pairing can be approximately computed from either SY or B XIs. So SY is trivial because by definition it's S of Y, right? But on the other direction, you have to play a little bit. S of sum of xi/gi is the sum of the xi S of gi by linearity. And then it looks like the dot product of the xi's with b, because the errors are small and the xi's are small. Okay. So I indeed obtain a pairing from lattices which can be computed if I hide any of the two inputs, just like in Diffie-Hellman. Okay. The only problem is that it's an approximate computation. Here it's not an equality. It's an approximate computation. So what I obtain is not exactly a Diffie-Hellman. It's a noisy key exchange, a noisy Diffie-Hellman key exchange. So this is the key exchange. So again, I retake Alice and Bob, and now they're doing something a bit more abstract. So they agree on some generators of the group. Alice selects a character and sends the LWE output, right? So she picked an error, and then she added to the evaluation of the character. Bob takes a short integer vector and send the SIS one-way function, so the sum of the xi gi. Send it to Alice. Now, by the previous slide, both Alice and Bob can compute an approximation of my pairing. And we have to decide on some rules. So Alice is going to perturbate S of y, and Bob is going to compute some of the xi bi directly. Okay? But indeed, you're convinced that now we have some kind of Diffie-Hellman-like lattice-based key exchange, except that it's noisy. So it's going to create some complications. But the good thing is that now I can obtain L-Gamal encryption, right? I have an L-Gamal encryption because any Diffie-Hellman key exchange gives rise to an L-Gamal encryption. But there's something funny. When you have Diffie-Hellman, you can only obtain one L-Gamal cryptosystem because the pairing is symmetric. If you swap Alice and Bob, you realize they're doing the same thing. But here, my pairing is not symmetric. On one side is dealing with characters, and the second side is dealing with integer vectors. So I actually obtain not just one encryption scheme, I obtain two L-Gamal encryption schemes. And that's why in the literature in cryptography, you see this regF encryption, but also the dual regF encryption used in the GPV identity-based crypto system. And the good thing is that these L-Gamal-like schemes are symmetrically secure under the harness of LWE and SIS, which is as hard as worst-case lattice problems. Okay? And naturally, the security proof is very similar to the L-Gamal security proof. So similarly, you can play. So I show you this game for trapdoor-less encryption. But you can play this game with many of the LWE SIS schemes by viewing them as analog of some RSA discrete log crypto system. So for instance, the famous GPV lattice signature scheme turns out to be an analog of Rabin signature. But you can do this game really with most of these primitives. OK, so this is just to give you a taste of lattice-based cryptography. So now we're going to come back to the topic of the conference, which is post-quantum cryptography. So we want to know what kind of concrete schemes have we. So these are the schemes that have been proposed so far concretely. For encryption, the oldest one is definitely untrue. So published first in '98. The parameters have changed quite a few times. Sometimes they use sparse keys, they use product forms. A lot of things have changed. Perhaps the biggest change there is when decryption failure attacks appear in 2003. But it's the oldest lattice schemes, and it's the one that resisted so far. Even though the parameters have changed several times, the core idea remains the same. This is perhaps the cryptosystem for which there is the most trust because of its history. You also see LWE schemes. So what is this? These schemes are ring variants of LWE scheme. So they are more efficient than LWE because they use special lattices just like N-true, but not the same lattices. However, you pay a price, you have a stronger hardness assumption. Just like N-true is also paying a price, we don't know how hard it is really to attack these special lattices. So these are things being instantiated right now in lattice TLS prototypes. Okay, so that's for encryption. Encryption is more or less clean. It's pretty efficient. This is some example. For signature, the situation is not as good. So for instance, if we take n-true, n-true signatures have been much less successful than encryption. The latest version of n-true signature was published 2 years ago at PQC. It's called MLS. And previous incarnation of n-true signatures have been completely broken. So first in the 2000 and then later on in the end of the 2000. We don't have so many proposals. So for instance, there's the well-known Bliss signature scheme published at Crypto 2013. And it used similar assumptions. I mean, the most optimized version of Bliss use n-true-like assumptions. Okay. So this is just some examples. There are plenty of other lattice schemes. But at some point, if there's a competition, there will have to be concrete proposals. It will be very interesting to see which encryption scheme is submitted and which signature scheme is submitted. So now in the last part of my talk, I want to tell you about the cryptanalysis of lattice-based cryptography. So when we're going to restrict ourselves first to algorithm finding short vectors. So there are essentially two categories of algorithms. Approximation algorithms, which are fairly efficient, and then exact algorithms, which are much more expensive. So they're going to be used only in reasonably small dimension. But let me just say that this is a classification, but more and more, these two things get combined now. Sometimes we now see exact algorithms being used to solve approximation algorithm and reciprocally. So the frontier is not so tight. For polynomial time approximation algorithms, it started with the algorithms, and then there is all this block generalization in the past 30 years. For exact algorithms, there's essentially two categories which you can see. Algorithms which are polynomial space, like enumeration and all the variants, pruning variants of enumeration. And then you have exponential space algorithms. So at this point, I'm going to ignore exponential space algorithms. These are the ones with the best asymptotics. But in practice, they seem to be beaten by these polynomial space algorithms. So there's a long literature now for all of these algorithms. But I want to make some remark. The first remark is what we're doing is very related to what has been studied in mathematics. So in mathematics, in lattices, a classical problem is to prove the existence of short lattice vectors. That means proving an upper bound on Hermit Constant. Okay? So this is perhaps the oldest problem in geometry of numbers. And for algorithms, we want to find short or shortest lattice vectors. So a natural thing to say is that if you have such an algorithms, somehow you must have a proof that this vector is short. So maybe implicitly, it's going to come up with some upper bound on the Hermit Constant. By finding such a vector, you prove the existence of such a short vector. Okay? And therefore, it's not that surprising that free mathematical inequalities have been turned into efficient algorithms. So the first one is Hermit inequality. That gave rise to the LL algorithms. Model inequality, which gave rise to blockwise algorithms. And the most recent example is Model's proof of Minkowski inequality. So there are two flavors. When you make this inequality into an efficient probabilistic algorithm, you can obtain either a worst case to every case reduction, either you obtain these new sieve algorithms, which can be viewed as a clean version of the original sieve AKS algorithm. Okay. So unfortunately, I don't have the time, so I will not talk about it. So I'm just going to say a few words now about these first two inequalities. And in case you wonder, we have more or less exhausted now all our mathematical inequalities. I mean, I'm not aware of other inequalities that could be turned into efficient algorithms. So it would be very interesting to find new mathematical inequalities on Hermit Constant, which may not be optimal, but that could be turned into efficient algorithms. So let's start with Hermit inequality. So what is the history behind this? The history goes a long time ago, back in the 18th century. So Lagrange, in a French article, he showed that in any two-dimensional lattice, there is a non-zero vector of norm less than this. So that shows you, that gives you the exact value of Hermit constant in dimension 2. It's a very famous thing. And Hermit in 1850 used this result to show that in an arbitrary, in a high-dimensional lattice D, there is always a non-zero vector of norm less than this. So you can see that this is exactly the d minus 1th power of Hermit constant here. So these are mathematical results first, proof of existence of short vectors. The good thing is that these papers actually came with algorithms. So Lagrange implicitly described an algorithm that efficiently outputs such a vector. So not only he showed the existence of such a vector, he showed how to find it efficiently. Okay? But remember that there was no computer, so he was not really interested in proving, doing a complexity analysis of this. But still, it's there. Similarly, Hermit also gave an algorithm, but this time we don't know if it's efficient or not. But he gave an algorithm to output such a vector. So it remained to see how we could find such a vector efficiently. So that's exactly what LLL did. So Lenstra and Slovach in 1982 show how to find a vector less than this bound. There's just a difference here. We have an epsilon approximation factor here. And the running time of the algorithm depends on this epsilon. Okay? So we somehow have to relax the bound, but it's really the same bound. So you can view, and you should view LLL as really an algorithmic version of Hermit's inequality, finding a vector satisfying Hermit's inequality. So I'm not going to describe the algorithm itself. I'm just going to say what is the intuition behind it. There's two big ideas in Hermit's inequality. The first one is projection. By projecting a lattice over suitable space, you create a lower dimensional lattice. You have to do it carefully because usually a projection of a lattice may not be a lattice. But if you choose your projection suitably, you have a lower dimensional lattice. So you try to solve your problem in this lower dimensional lattice, but you have to come back to your original problem. So you have to lift a short projected vector. That's the second idea behind Hermit's inequality. So what did LLL add? LLL is actually very similar to Hermit's algorithms. The only thing that changed is it added some relaxation to guarantee polynomial time. Okay? So one good thing about LLL that has been noticed for many years, soon after the introduction of LLL, is that it somehow performs better than what you would expect from the theory, from the worst case bound. So to give an example, this factor that comes from Hermit's inequality are only tight in the worst case. That means they only apply for worst case bases of certain lattices. Experimentally, once you randomize the basis for any lattice, you find a much shorter vector. So what does it mean exactly? I take this graph. This is the upper bound on the size of the norm of the vector found by LLL. And this is what you get in practice. So of course, it varies a little bit, but it's really around this curve. So it's both better and not that much better in the sense that it's better, yeah, the slope is much better, but it's still exponential. So what it means that in practice, it's as if instead of having 4/3, you have something replaced by this. So there's still no good explanation for this phenomenon. And more importantly, there's no known formula for this experimental constant. Okay? So we don't know, we don't have any explanation. Why is it something close to 1.08 and not something like 1.06 or whatever? Okay? But this is something that everybody has experienced when playing with LLL. OK, so now I'm going to switch to model inequality. So I'm just going to give you, again, the intuition. So without describing LLL, I still said that it's based on projection and lifting short projected vectors. So actually, LLL, you can view it as based on a local reduction in dimension 2, just like Hermit was doing with Lagrange's result. So the natural thing to do, if you know that LL uses dimension 2, is to say, OK, I'm going to replace 2 by something bigger, not too big so that it's still doable. And hopefully, I can find shorter vectors by doing something a bit more work in low dimension. So that's exactly what they do. Blockwise algorithms find shorter vectors than LL by using some subroutine to find short vectors in a low dimension called the block size. So you could think that LLL use k equal to 2, which even though it's not exactly the case. And now the trick is, if this routine is expensive in k, for instance, suppose that it's exponential time in k, you can still make it polynomial in a dimension if you choose k sufficiently small, like logarithmic in a dimension. Okay. If you choose a bigger function, then you would get sub-exponential time, for instance. Okay. So again, I'm going to make this mathematical analogy. If I could show the existence of very short vectors in dimension k, can I use it to prove the existence of very short vectors in much higher dimension? That's a topic that has been investigated by Mordell in 1944, a very short paper. When he generalized Hermit inequality, he obtained this inequality. Square root of the Hermit constant is less than square root of the Hermit constant in dimension k raised to this power. So that means that in any lattice L, there is a vector of norm, a non-zero vector of norm bounded by this quantity. So a natural thing to think would be, can I find a vector satisfying this using a subroutine, finding short vectors in dimension k? That would be the natural bound. So this is exactly what's happening. So LLL corresponded to Hermit inequality. It finds a vector essentially as short as this bound. And the slide reduction algorithm of 2008 find a vector as short as the Mordell inequality using some k-dimensional oracle. Okay. So how does it work? So first, you can see that Hermit inequality is really just a particular case of Mordell inequality. So it's not surprising that it was going to use something similar. The interesting thing is that all the proof of Mordell inequality which are known use at some point duality. So the algorithm that achieve these kind of things also use duality. And I'm not going to enter into details, but I'm just going to say that before I said LLL use projection to reduce the dimension of a lattice, this algorithm using duality use duality to decrease the lattice dimension in a different way. Okay, so that's a different aspect. But again, what is interesting is that the algorithms are connected to the mathematics. It's not something independent. So this is the recap. You can solve this Hermit SVP problem with factor essentially this using a k-dimensional oracle. And now using known routines for this oracle, you can get a polynomial time algorithm with a sub-exponential approximation factor by plugging your best exact algorithm here. Okay. So this is just a snapshot of lattice algorithms. There are many more lattice algorithms. 1 hour and a half would definitely not be enough to cover all these algorithms, but I hope I did give you a taste of what it looks like. So now, for the final part of this talk, I want to talk about a very tricky subject, but unfortunately a major importance to post-quantum cryptography is security estimates. So I think that's a common problem with all the post-quantum proposals, if we accept a hash-based proposal, how to make meaningful and trustworthy security estimates for our post-quantum primitives. And I think one of the point of that section would be that all these post-quantum proposals use a lot of parameters. I mean, in RSA, you essentially only have to select the bit length of the numbers. So we can easily compare, more or less easily compare algorithms, even though that is not even trivial in this case. But once you have a crypto system that uses 10 or 20 parameters, it's very difficult to know what's going on. In particular, you cannot really select by hand the parameters. You have to run some algorithm. So this is what we know. So back in the 80s and 90s, you could say that lattice algorithms were really somehow a dark art. And many people said, I mean, the algorithm performed better than theory expected, but nobody really dared to say by how much. Not because they didn't want to, but it was very difficult to get a clear picture because we were limited by computational power. And maybe at that time also people were not so interested to know how good the algorithms were. Okay? We didn't have lattice crypto system at that time. So why is it so difficult? So first, unfortunately, theory is great, but sometimes theory is really insufficient. And the reason is because in theory, we only care about worst-case analysis. And worst-case analysis are often a poor explanation of what's going on in practice. So unfortunately, for cryptography, we don't want just a worst-case bound. We want to know what's going on in practice. So we would like to do something crazy. We would like to predict the running time. So that's obviously much more difficult. So let's not be too crazy. We will not be able to predict by a microsecond the exact running time. What we want to know is essentially the order of magnitude. Okay? It would not be meaningful to pretend something more, something better than that. The other problem is that these security estimates are somehow independent of security proofs. Security proofs are very useful. They give you a lot of valuable information, but they may not tell you exactly how the system is secure in practice. So we want to identify the best attack based on the state of the art. So we're left to do something very stupid, which is find as many attacks as possible and identify the best one. And once you have many parameters flowing around, it becomes very problematic because you have like maybe 20 or 30 different algorithms. You have to fine-tune it with maybe 10 or 20 parameters, and then you're really, it's not an easy task. So in order to see things more clearly for lattices, it's very good to be able to reduce it to a core problem. So we want to understand what is the central problem in lattice algorithms. So for now, the most popular core problem is the following problem, which we call a Hermit approximate SVP problem. You're given a basis of some lattice, you're given some approximation factor, and you want to find a non-zero vector of norm less than this bound. So the good thing about this problem is that everything is concrete. Everybody can compute the volume. Everybody can compute f of n, so everybody can check whether this is true or not. This is sometimes not true for other lattice problems. And the good thing also about this problem is that you can really compare things. So for instance, suppose you have found a new algorithm and you want to know how good it is. Then it's a very simple thing to do. Pick a random lattice, run your new algorithm, measure B1 divided by the d fruit of the volume, and then see what's going on. See how good is your algorithm. Typically what you get that this measure would be exponential in dimension, but sometimes if you find a much better algorithm, it will be something different. So this is a very simple experiment. And based on that, we try to derive security estimate for the main lattice problem, for SIS, for LW, and so on. We try to factor everything in terms of the Hermit factor. Are we successful? So we're successful for many lattice problems, but not all of them. A particular problem is n-true. So n-true use very special lattices for which the secret key has an influence. How sparse is the secret key? As far as I know, there's no clear conjecture relating the honors of solving the n-true lattice using the Hermit factor. There are some estimates, but not a clear conjecture. So I think it would be very useful if the entropy people would formulate such a conjecture. There is some experiments in the Bliss paper that try to relate this Hermit factor to the hardness of solving entropy lattices. But it would be very nice to have a clear relationship between the two, even a heuristic. I mean, obviously it's going to be heuristic. So once if we reduce everything to a core problem, everything becomes a bit more simple. So how would we do that? Well, now we want to assess the efficiency of an arbitrary lattice attack. So if you can relate everything to the Hermit factor, we know how good should be the Hermit factor for this method to work. And depending on this Hermit factor, depending on the target, we see which algorithm is mandatory. Is LLL enough to solve this Hermit factor? If not, try to guess which block size should be enough to solve this problem. And again, we're not there to give a very precise estimate. That's completely hopeless. We just want an order of magnitude. Is it 64-bit secure or is it 128-bit secure? This kind of thing. So for a long time, it was not clear what would be the performances of BKZ for a very high block size. But now it's more or less possible. So it is possible to predict approximately the behavior of high block size BKZ or over block-wise algorithm using some kind of simulation. So for instance, we can try to guess what would be the performance of BKZ 200, even though we don't have the computational power to run BKZ 200. So how do we do that? This simulation algorithm is based on a very simple assumption. We're assuming that the minimum of certain k-dimensional lattices related to the algorithms behave like random lattices. So using this assumption, you can really make prediction. And what we have observed is that these predictions match what we can do up to, say, block size until 100. So of course, it would be very nice to do much bigger experiments. To confirm our theory, it would be very nice to do a much bigger block size and check whether things are still going OK, because it's quite a conjecture to say that it's going to behave exactly like this. Okay? But at least there is a model. Before that, people used to do extrapolation of running times, extrapolating both the running time and the quality. I think that's much more debatable. So I prefer to do this kind of assumption than extrapolating running time or extrapolating graph. So essentially what it tells you is that if you run a high block size algorithms, what you get is the Gaussian heuristic raised to this exponent, the same as model inequality. So you replace Hermit Constant by the Gaussian heuristic. So maybe this is a bit shocking. The good thing is that these shocking things have been done before. We know that, in particular in factoring, when people analyze sieve algorithms for factoring, like a quadratic sieve or a number field sieve, they do something similar. They don't know how to completely rigorously analyze their algorithms. The analysis assume that certain numbers produced by the algorithm behave like random numbers when it comes to smoothness probability. So they have these random numbers. They don't know their distribution. They're going to say, this random number is going to be smooth with the same probability as a true random number of the same size. That's the kind of things that they're doing. So what we're doing is the same thing by replacing numbers by lattices. Okay? So to illustrate, how does it look like? For instance, this is the target Hermit factor you would like to have. Say you want to find a vector as short as 1.008. So if you believe in this theory, then you can see that the approximate block size required to find this is 133. Again, don't take this too seriously. It's written 133. It doesn't mean that if you take 132, it's not going to reach this. This is an order of magnitude. So you should never take things completely like, sometimes I see some security estimates when they put some digits here. I think this is really not consistent with what we know. We don't want, our estimate is not going to be that precise. This is just for having an order of magnitude. It's better than knowing nothing. Okay. So this way, we know roughly what is the approximate block size. For instance, if we know that to reach 1.006, we need roughly a block size around 200. Okay. So we are interested now in knowing how much costs this block size. So this is where it gets a bit crazy. So we'd like to estimate the cost of this subroutine. And this is where optimization is particularly difficult. And you can see from challenges that there has been quite a lot of progress in the past few years. So what is the problem? So in current implementation, there are several implementations that use pruning enumeration for this subroutine. And we know reasonable prediction for these subroutines. I mean, when we fix all the parameters, we know roughly how long it's going to take. The problem is that there are so many parameters to select, but you don't know if what you selected is really optimal. Maybe there's a better way to do it. So that's why actually in our paper between the full version and the preceding version, we updated the upper bound. The interesting thing is that also in our paper, we gave some lower bound based on mathematical results, and we saw that there was a huge gap between the upper bound and the lower bound, which suggested that there could be a lot of progress in this subroutine. So let me be clear. These are just upper bound. It's not a lower bound here. Sometimes I see papers using it saying this is the cost. No, this is not the cost. This is just an upper bound on the cost. Maybe it's much lower than this. We never claim that this is the actual cost of doing 140. We know that it's not going to cost more than 64-bit. But maybe it's going to be, could be significantly lower. So this was the table we got in 2011. We got a lower bound and upper bound. I didn't put the lower bound here because there was really a huge gap. But it tells you that there could be a lot of progress here. And the best way to check the progress is to look at concrete computation. So there's something called, there's a popular online challenge called the SAP challenge, and you can see how much it costs to find not exactly the shortest vector, but a very short lattice vectors. Say 1.05 times the norm of the shortest vector. Okay, so this would be equally as good if I plug it into BKZ. So this gives you a good indicator, if we trust the running times here, of how much it really costs if we try to optimize things, even for this again could not be, may not be optimal. So these are the running time reported by the people who solve these challenges. And so for sufficient high dimension, everybody using some kind of enumeration. So classical enumeration, and then something called, I would call discrete pruning here. And this is the running time reported, and you can see this is the curve here, and this is the curve here with different strategies. So is this method better than this one? It's unclear. We don't have enough points, but it's not going to be a huge change. What you can see is quite interesting, though, is that here, sometimes decrease, sometimes increase. You can see that fine-tuning the parameters is not trivial. And that's what I said before. In all our best lattice algorithms, there's so many things you have to change to select. How do you do it the best way? It's very not an easy thing to do. Let's compare this running time with other situations. So the largest computation used for the SVB challenge is for dimension 138, where people reportedly use 66,000 core days. That's 2 to 63 clock cycles. That's about 10 times cheaper than the RSA 768 computation. So the amount of computation used for lattice challenges is still much less than what has been done for RSA. But what is interesting is that if you look at the number of, for instance, 140, you can see that the effort of 140 corresponds to about a 53-bit secret key. And before, remember our upper bound, the upper bound back in 2011, we said that it was less than 64-bit. Now we see it's much less than 64-bit. It's essentially 53-bit. And even that computation may not be optimal. So you have to be really careful when you say this costs this costs that. So I wish there's a lot of now people trying to select parameters. You should be really clear which assumption you're going to make. What is the block size required? What do you assume on the cost of the block size based on what computation? So what is the state of the art? So the state of the art right now is we understand reasonably well the best lattice algorithms in the following sense. We don't know everything, but we can guess the approximate quality and the approximate running time once everything is selected. Say you're going to use, I'm going to use BKZ with block size 120 with a pre-processing using BKZ 80, blah, 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 blah. If we choose everything, we have a fairly reasonable approximation of what's going to happen. However, what we don't know is how to optimize this selection of parameters. People used to do an exhaustive search on the parameters, but there's just too many of them. So we don't really know what's going on. And the other thing that we realize is that there is a big gap between the lower bound and the upper bound. So even if we restrict to a particular kind of algorithms, we know there could be progress. And if you look at the latest SVP record, you see there's some kind of progress. They use a different form of pre-enumeration, which may or may not be better, but at least you see that things are changing slowly. So what does it mean for us? So it means that it's better to be conservative. It's better to take a security margin. We should not just take the latest upper bound from that paper to say this is the bit security level. This is not meaningful. We have to be very careful when we make this security estimate, especially when we're targeting very high security levels like 256-bit. I mean, that's really scary. And we have to realize that this situation already happens for crypto systems which we understand better, like RSA. I mean, if you look at the security estimates for RSA, they vary from one source to the other. Even for the methodology could be similar. They try also to model the progress in hardware. These kind of things we need to do for lattices. Okay? The good thing is that if you look at the target Hermit factor here, you can see that even if there's a lot of progress, suppose that now a 170 dimensional thing can be done is the same cost as a 130. In the Hermit factor, it's not a huge difference. Okay? So asymptotically, it should still be OK. One issue, though, that I have is that if you consider lattices for which the dimension is not that much bigger than the block size, it's not clear if our estimates are really trustworthy. I mean, we don't have enough experience with these things at that point. And that's why the competition is really useful. We're going to find out what's going on in the next few years. OK. So I really want to stress it's extremely important for any of these post-quantum crypto systems to have numerical challenges. Not because we're very excited to solve the challenge. Finding this short vector in this particular lattice, no, that does not excite me. What is interesting, though, is to check, to perform a sanity check on our state of the art. Do we really understand things well? This is the best thing to do. We do this computation. We check that the running time is consistent with what we expected. If nothing goes weird, we are satisfied, and we have more trust towards our security estimates. So, for instance, for Entru also has some challenges, and the dimension of the lattice corresponds to the doubling of this number here. And again, I think it's extremely important to understand better the security of Entru to have these challenges. So, for any scheme, I would really recommend people to put forward some challenges. With or without money, that's not really relevant, but it's more about trying to check what we know. Is it really consistent? So I hope you will survive this 1 hour and a half. So now, fortunately, it's coming to an end. There's one thing you should remember from this talk. So RHA discrete log cryptography works with certain finite abelian groups. And lattice cryptography works in different groups, quotient groups of the form the integer vectors divided by some lattice. The trapdoor is, in some sense, a secret representation of this group. And remember that this group turned out to be bigger than the original group, but has cheaper operation. If we make this analogy, we also realize that the noise, there's a lot of noise in this lattice construction. we also have this notion of small preimages, and they're required to adapt the construction, in particular the security proof. But there is really an analogy. So I would say that lattice cryptography is different from classical public key cryptography, but there's also many similarities, and it's good to be aware of them. I think that making analogies will hopefully help our understandings. There's a couple of natural questions. More and more classical public key schemes are being adapted to the lattice settings. Can all of them be adapted? Reciprocally, a few lattice schemes achieve new functionalities like fully morphic encryption, multilinear maps, general attribute-based encryption. Can they be achieved without lattices? These are very natural questions. Coming back to cryptanalysis, so we're really concerned about the quantum security. So I would say the field is really open, because if you look at, going back to the literature after Shor's article, there are still very few examples of quantum algorithms. And especially when we restrict ourselves to cryptanalysis. Count the number of people who are seriously working on quantum algorithms. Count the number of people looking seriously in lattice algorithms. These are very small numbers. Now you take the intersection of two small sets, it's even smaller. So we really need more people investigating these questions. And there's another thing, which is I believe that we won't really know the true power of quantum algorithms until we really have a quantum computer to play with. Why is that? Because right now we're restricting ourselves to provable algorithms. But our experience with lattices shows that it's very interesting to also consider heuristic algorithms. But how can you guess the behavior of a heuristic algorithm unless you implement it, unless you really know what's going on in practice? That's going to be very hard to do without a quantum computer. So I think the end-line question will only be answered when we have toys to play with, once we can play with heuristic algorithms and not just theorems. And then brings us to a difficult question. How confident are we that our problems are resistant to quantum computers? This question is for lattice problem, but also for other post-quantum proposals. If you look at the most efficient lattice-based proposal, they all use ideal lattices to make the scheme more efficient. That comes at a cost. The security assumption is different. It's a natural question, but still, it's a stronger assumption. How much can we trust our security estimates in this case? I mean, this is really a difficult question. And how precise are they? Again, I told you there are very few people that work in both quantum algorithms and these lattice algorithms. If you restrict now to ideal lattices, it's even a smaller quantity. But on a positive note, I would say that what is going on is really a revolution. I think there's a lot of exciting work to do, especially for young people here. I'm too old to solve these questions, so I hope you will find this, you will solve these challenges and find new algorithms. I would not be surprised at all if there's much better algorithms coming in the next 5 years in lattices. Thank you for your attention, and I would be happy to answer any question.
Thank you very much. Is there any questions?
I was wondering about now that we have a better understanding of lattice problems, how difficult they are, does that kind of give us the right way to tune the barometers for LWNs, or is that going to be like a completely different research?
Sorry, what is?
So now that we have like a better understanding of like when the dimension is this big for our lattice, we have this much security level. Like, does that give us a direct way of setting the modulus size of LW or the error distribution size, or is that another research topic that we would have to think about?
So I think this question is very important. And actually, this has been investigated in the past few years. So some people who propose parameters now are kind of doing these things. But until we see some concrete sets, I think we won't really understand the situation until really there's some concrete targets. There's so many flexibility in LWE. How do you choose the noise? Which distribution are you going to choose? How are you going to choose Q? How are you going to choose N? We cannot ask the cryptanalysts to figure out all by themselves. So I think, as was done for other public key crypto systems, some people have to propose a few parameter sets, and then we're going to study them really intensively. That's how we're going to discover what's going on.
One more question? More question? No question. Okay. Let the speaker again.